Now in this lecture, we are going to study the change of the basis and the unitary operator. Unitary operator. Suppose that we have two incompatible, that means a comma b not equal to 0, two incompatible operator, and both of these operators are Hermitian. That means corresponding to both of these operators, we can have a orthonormal eigenkette set, that is A and that is B. Now with these two set of orthonormal eigenkettes, we can expand the same basket. For example, for spin half system, plus minus S set may be used as baskets or plus minus Sx may be also used for the baskets. Now the two different sets of baskets of course span the same K space. We are interested in finding out how the two descriptions are related. That means this description and this description is related to each other. Now changing the baskets are referred to as a change of the basis or a change of the representation. Change of the basis or change of the representation. The basis in which the basket are the eigenkettes of the operator A. That basis is sometimes called A representation, the A representation, or it's sometimes called A diagonal representation. Why A diagonal representation? Since in this eigencase A is diagonal matrix, so that's why it is called A diagonal representation. Our basic task is to construct a transformation operator U that connects old orthonormal eigenkettes gate set, suppose A, with the new orthonormal gate set B. To this end, we first show the following. There is a theorem that corresponding to that transformation operator, the behavior of the transformation operator. The theorem is given to sets of base case both satisfying one orthonormal condition and to the completeness relation. Then there exists a unitary transformation U such that U bk equal to U ak equal to such that U ak equal to bk for all k. Now here B is the new orthonormal gate set and A is the old orthonormal gate set and U is the transformation operator that transform these bases to a new another basis. By unitary transformation operator means U dagger U equal to U dagger equal to unitary operator. To prove that theorem, let us assert that operator U has the form summation of k bk ak. This operator follows that property, this property. How we can see that? If we operate ak, it will al, it will give us back bk ak al. Since this is orthonormal k vectors, that means ak al is delta kl, bk delta kl, which is equal to bl. That means this operator follows this property. Now let us check whether this operator is unitary or not. That means U dagger equal to summation of k bk ak into summation of l bl al dagger, which is summation of k AK summation of L AL PL, which is nothing but summation of K comma L PK AK AL PL. That means summation of K comma L PK delta KL PL, which is nothing but summation of K PK. Since this eigenkate is also orthonormal and this eigenkate follows the completeness relation, that means this equal to identity operator. That means U dagger equal to identity. Similarly, we can prove that U dagger U equal to identity. That means U is a unitary operator. Hence, we prove that this theorem, that if the two set of orthonormal gate vector which follows the completed relations, then there exists a unitary transform U such that U AK equal to BK. Now let us see that the matrix representation of the transformation operator U. In A basis, which is the element of that matrix UKL equal to AK UAL, which is AK PL. This is the matrix representation of that operator U. As we know that we can represent any arbitrary gate vector in both bases, in basis of A or in the basis of P. Now let us ask the question how the coefficient of alpha in the old gate basis relates with the new gate basis. That means what is the relation between BK alpha and AK? To do so, let us first expand alpha in A basis. Summation of K A alpha. This is the coefficient in old basis. Now what is the coefficient in the new basis? That will be PL alpha equal to PK PL here will be a K AK and AK alpha. This is nothing but K AL U dagger AK AK alpha. How we get this? We know that PL equal to U AL and its dual correspondence will be PL equal to AL U dagger. So the new coefficient, that means this new coefficient will be U dagger in the matrix form into the old coefficient. If in the matrix representation this arbitrary eigenket vector will be a column matrix, and any element of the column matrix is the coefficient corresponding to that particular basis. So the new coefficient can calculate it from the old coefficient from this formula. New coefficient will be U dagger in the matrix form into the old coefficient. Now we will see the relationship between the old matrix element and the new matrix element. Suppose any operator X, we can represent this operator in both of these bases A and B. Now let us ask the question, what is the relation between the matrix element in the basis B and in the basis A? Now the matrix element in the basis B will be pk x pl, that will be x k. Let us use the complete trace relation of this base case, summation of m a m x summation of n a n pl, that equal to summation of m comma n bk am x an into an pl. This is equal to m comma n ak u dagger am x an u al. So this is simply the well-known formula for the similarity transformation in the matrix algebra, which is x prime equal to u dagger x u, where x dagger is the transformed new matrix, and x is the old matrix. This matrix is represented in new basis set, and this matrix is represented in the old basis case. Now let us ask the question, what happened to the trace of x? What will be the trace of x in the two basis system, in the two basis set? One is A, another is B. So trace of x will be summation of k ak x AK. Now let us use the completeness relation of the kth vectors pk. Summation of k ak summation of l pl pl x summation of m pm pm ak is equal to summation of k ak klm ak pk pl x pm pm ak. Since these two are complex number, we can interchange its position. That means k l m pm ak ak pl pl x pm is equal to l comma m pm sum over k ak ak pl pl x pm, that is equal to l comma m pm. Since this is the this is identity operator, that means pk, that means this equal to identity operator pl x pm, which will be, since these k's are orthogonal eigenkets, that means this equal to l comma n delta lm x pm, that is equal to summation of l pl x pl, that means trace of x in the coordinate system P, in the basis P. Actually the basis is similar to the coordinate, so a trace is reserved, trace is not change, trace is not change, is not change if we change the basis. This is an important property. Now let us see another theorem. Let us see another observable, which is called unitary equivalent observable. Suppose that the two orthonormal eigenkets are related through a unitary transformation U. Then that is U AL equal to PL. These are the eigenkets. This is the eigenkets of the operator A, of the operator A. Then the theorem is, then the BL will be the eigengate of the operator B, which is U A U dagger, which is nothing but similarity transformation of the operator A. Now let us prove that. Since AL is the eigengates of the operator A, that means AL will be AL, okay? And here in this BL will be the eigengates of the operator, not only the eigengates of the operator, this operator, the corresponding eigenvalue will be same. Let us see that. L. Now operate B on PL. What will get? U A U dagger into U A L. Since U is an unitary operator, U is a unitary operator, then U A L, this is equal to identity operator. That means U A L, since AL is eigengates of AL, PL, since U AL, PL. That means BL is an eigengate of the operator B with the same eigenvalue L. Same eigenvalue L. Now, as an example of a transformation matrix, let us study translation operator tau tx, which is infinite small translation operator. So what it does? Suppose we start with a state that is localized around position x, then the translation will change the state in another state which will be localized around a position x plus dx. That means, and with everything else unchanged. Mathematically, this means the translation operator dx operate on x, it will change its state to x plus dx. Let us see the effect of this translation operator in an arbitrary state alpha. So, if we operate dx in alpha, let us see what we will get. To do so, first we have to expand this alpha in terms of the base cat x. So, if we do so, that means alpha will be integration dx x alpha. So now if we operate tau dx x alpha, it will change the state to x plus dx to x alpha. It means tau dx shift the coordinate of the system by infinitesimal dx amount. Shift the coordinate. Now we will list some property of this translation operator. Property number 1, that it is reasonable to require that if the ket alpha is normalized to unity, the translated ket should also normalize to unity. That means alpha should equal to alpha tau dagger dx tau dx alpha. That will be followed when tau dagger dx into tau dx will be equal to identity operator. That means this tau is a unitary operator. Now second property. Two successive infinite small translation first by dx and then by dx prime we expect net result to be just a single translation by an amount dx plus dx prime. That means tau dx into tau dx prime should equal to tau dx plus dx prime. The next property, the third property, is translation in the opposite direction. Translation in the opposite direction is the same as the inverse operation which is done by the translation. That means translation in the opposite direction minus dx should equal to inverse of dx. And the fourth property is that infinite small, that for the limiting case translation operator will be unitary, it will be identity operator. That means limit dx tending to 0 tau dx should equal to 1. That means when there will be no translation, that means that is equivalent to say that the state does not change. That means the limit dx tending to 0 tau dx equal to 1. Now let us assert that tau dx is equal to 1 minus I k dot dx, where k is a Hermitian operator. Now check whether this operator follows the four following property. Now property number 1, that it is should be a unitary operator, that is tau dagger dx into tau dx equal to tau dx tau dagger dx should equal to 1. Let us check it. Now tau dagger will be 1 plus I k dagger dot dx dagger, which is nothing but 1 plus I k dot dx. Now tau dagger dx into tau dx equal to 1 plus I k dx into 1 minus k dx I, which is equal to 1 minus I k dot dx plus I k dot dx minus k dot dx square. If we ignore the second order term of the dx, since dx is infinite small, it is very small, then we will get 1. That means tau dagger dx into tau t is equal to 1. Similarly, we'll get tau dx into tau dagger dx will be 1. That means tau is a unitary operator in the limit of when dx is very small. Now let us check that this form of this translation operator follow the second property, which is the two successive infinite small translation, first by dx and second dx added up. That means this property. Property number 2. Tau dx prime. This is equal to 1 minus I k dot dx into 1 minus I k dot dx prime, which is 1 minus I k dot dx minus I k dot dx prime minus k dot minus k dot dx into k dot dx prime. Since this is in the second order in dx, so we can safely ignore this term. Then we will get 1 minus I k dot dx plus dx prime. So that means equal to tau dx plus prime. Now the form that we have taken for tau dx actually follows the second property as well. Now let us check, is it obey the third property? That means tau minus dx is equal to tau inverse dx. Tau minus dx equal to 1 minus I k dot dx, which is equal to tau dagger dx. Since we know that tau dx into tau dagger dx equal to tau dagger dx, tau dx equal to unitary operator, that means tau dagger dx is the inverse. That means the form that we have taken is also follows the third property. And let us check the fourth property, that is limit dx tends to 0 1 minus I k dot dx is equal to unitary operator. That means it also follows the fourth property. That means we can take tau dx as follows: 1 minus 1 minus k dot dx. Now by accepting the form of the tau dx, we are in a position to derive an extremely fundamental relation between the operator k and operator p, which is the momentum operator. momentum operator. So to do so, first let us derive the commutation relation between the position and the translation operator. X tau dx x will be x plus dx. That will be x plus dx into x plus dx. Now in the inverse direction, tau dx into x will be tau dx into x. That means x into x plus dx. If we subtract these two equations, we will get this equation and this equation. We will get x tau dx minus tau dx x is equal to dx into x plus operating on x will give dx into x, that is equal to dx x. That means the commutation relation between these two give back dx. Now from this commutation relation, let us derive the commutation relation between x and the momentum generate the infinite small translation generator operator k. To do so, let us write x into 1 minus I k dot dx minus 1 minus I k dot dx into x, which equal to dx. Now, which is, if we multiply now this equal to x minus I x k dot dx minus x plus I k dot dx into x to dx. Now if we multiply both sides of the equation by x cap, the unit vector along the z direction will get x dot xa into k dot dx minus k dot dx into x dot xa dx dot xa cap. This implies summation of I xa ki d dxi minus ki xa dxi is equal to dxa. That is nothing but summation of I delta ij dxa. From this equation we'll get that xa ki minus ki xa equal to delta ij. That means, there will be I in this side, I. So that will be xj comma ki equal to I delta ij. Now, physically, let us think that what else can generate the infinite small displacement other than momentum operator? So, this this infinite small displacement generator operator k should proportional to the momentum order p, but the k dot x is dimensionless quantity. That means p dot p dot x has the dimension of the angular momentum. So k should be equal to some constant c into p, and it is happen so this c is equal to p by h cut. H cut is the dimension of h cut is same as the angular momentum. Now that means from this commutation relation we know that x j comma pi by h cut, xj by pi by h cut will be equal to I delta ij. That means xj comma pi equal to h cut, which is the commutation relation, famous commutation relation between the position and momentum operator. Now, as we studied in the previous lecture, that if there is a commutation relation between two observable, there will be uncertainty while observing these two while measuring the position and momentum subsequently. What will be that uncertain relation? Then what will be the uncertain relation? That uncertain relation will be delta xa delta xa square into delta pi square should be greater than equal to delta ij h cut square by 4. That means delta xi square delta pi square should greater than equal to h cut by 4. This is the dispersion or the fuzziness if we subsequently measure position and momentum. Then that fuzziness or uncertainty in the measurement corresponding to the x and p should follow this relation, this uncertain relation. This is the famous uncertainty relation between position and momentum. So, thank you.